Those were the days when the pleasures of motoring were enjoyed by a very small section of society. Days when ownership of a new car was everyone's dream, a major milestone in your life, something that would start the whole neighborhood talking. Something limited to the privileged few. When a major service was needed every 3,000 miles, a minor one every 1,000, and a comprehensive check before undertaking a tour of 20 miles or more, fuel economy was a minor consideration in the overall running costs. Society grew more affluent, and volume production made the car an achievable reality for the man in the street. As the humble motor car's role changed from being a symbol of status and privilege into an everyday workhorse, worldwide economic pressures increased the cost of motoring, and fuel economy began to play a major part in purchase decisions. Competition between manufacturers increased, and in today's world, if you want to survive and prosper in the volume car business, it's not enough to have an attractive model range. You need to offer the customer excellent fuel economy and performance as well. Fuel economy means fuel control, planned and calculated control, to give a total fuel management system and help the driver get maximum economy and optimum performance from his motor vehicle. This program's been produced to give you an insight into the carburetor fuel management systems used on the majority of models in the current Austin Rover range. We'll be looking at the systems fitted to the Maestro, Montego and Rover 216, which incorporate a single HIF44 carburetor, which should already be familiar to you. We'll also deal with the twin HIF44 carburetors fitted to the 1985 model year Rover SD1. During the program, we'll discuss their basic operating principles, the tuning adjustments and fast check fault diagnosis necessary for their efficient operation, and also give tips to help you diagnose problems you could encounter in service. Whether employing single or twin carburetors, the principles of the fuel management system are the same. During this section of the program, we'll be looking at the 1.6-litre S-Series fuel management system and its application in the Montego, but the points made apply equally to all Austin Rover models fitted with this type of fuel management system. We'll highlight differences in operating principles between single and twin carburetor installations as they occur. The principal components of the fuel management system are the air temperature control system, incorporating a thermostatically controlled inlet manifold heater, the electronic control unit, which operates on signals received from the coil, the ambient air temperature sensor, the coolant temperature thermistor, and the throttle switch. With the HIF carburetor incorporating a fuel cut-off valve, a vacuum valve, and a stepper motor operating a rotary choke and a throttle jack. We'll begin this section on basic operating principles by considering the air temperature control system, the purpose of which is to ensure that air entering the engine remains at the optimum temperature for highest efficiency, irrespective of operating conditions, to improve drivability when cold. This is achieved through the use of a Thermax switch in the carburetor plenum chamber, which operates a spring-loaded air flap located at the base of the separately sited air filter. This flap controls the temperature of the air entering the engine via the filter. Although between models the location of the Thermax switch or air bleed valve may vary, they all operate in the same way. When the engine is first started, manifold depression, operating via the Thermax switch, moves the air flap against spring pressure, closing the cold air intake and allowing only warm air to be drawn from the exhaust hot box around the manifold. Once the temperature of the air passing through the plenum chamber reaches approximately 30 degrees centigrade, a bimetallic strip within the Thermax switch begins to operate, venting the depression to atmosphere. This reduces the depression acting on the air flap, allowing spring pressure to move the flap down, shutting off the hot ducted air and opening the cold air intake. Now here's a quick way to check the system's functioning correctly. First, with the engine cold and running, remove the vacuum pipe from the diaphragm. The flap valve should be heard to close. When the engine reaches operating temperature and is running, remove the vacuum pipe again. This time, no flap movement should be heard. An important point to note here, if the pipes are removed from the Thermax switch, make sure the pipe from the flap valve is fitted to the connector without the restrictor. If it's not, the result could be an extended warm-up period and poor drivability from cold. To maintain air-fuel mixture temperature, the inlet manifold has a hot spot heated by engine coolant. And to further aid drivability, especially from cold, the manifold also incorporates a thermostatically controlled electric heater which operates until the coolant temperature reaches 55 degrees centigrade. To control the mixture strength during cold running conditions, according to ambient and engine temperatures, and provide total fuel management, an electronic control unit, or ECU, is used. Information is received by the ECU from a number of sensors, providing data on ambient air temperature, coolant temperature, engine speed, and finally, whether or not the accelerator is fully released, sensed by a throttle pedal switch. The ECU continually analyzes the changing information received from the various sensors and in turn sends signals to 1. The fuel cut-off valve, which operates during certain overrun conditions to provide additional fuel economy, and 2. The stepper motor, which controls engine idle and fast idle speeds and enrichment during cold start and engine warm-up periods. We'll now examine the components of the fuel management system in more detail. The stepper motor is mounted on the side of the carburetor and essentially replaces the more traditional manual choke. This graph represents a fairly typical fuel consumption return when a manual choke is used as an engine warms up from cold to normal operating temperature. The vertical red line represents normal engine operating temperature, and the steps represent the choke returned in stages by an average driver. When we introduce a graph representing an electronic choke used under the same circumstances, the differences between the two and the subsequent fuel saving of the electronic choke are quite apparent. Apart from the additional fuel used unnecessarily when the choke controls pulled out too far on starting, not returning it early enough as the engine warms up also wastes fuel. The ECU-controlled electronic choke, on the other hand, gradually reduces cold start enrichment economically without impairing drivability, and a fuel gain of around 5% is obtained compared with a manual operation. And where the manual choke is clearly misused, the gain in using an electronic choke is even more significant. The rotary choke consists of a spindle and a sleeve. The spindle's connected to the cam wheel, which is turned with the stepper motor pinion. Air from an inlet and fuel from the float chamber are drawn through the carburetor body into an orifice in the sleeve, where it emulsifies into a fuel-air mixture before entering a port in the spindle. A V-shaped slot is machined circumferentially from the port around the spindle. So, on instructions from the ECU, the spindle turns in a closing direction, and the size of the orifice created between the two ports reduces progressively, decreasing the air-fuel enrichment smoothly and steadily as the engine warms up. There are 5 connections from the stepper motor to the ECU, 1 common and 4 returns. By earthing various combinations of these returns, the stepper motor is made to move in steps of 7.2 degrees with a maximum movement of 3 complete turns, which, through reduction gears, gives 120 degrees of choke movement. The first 40 degrees of movement operates the throttle jacking and fast idle facility, both of which we'll cover later in the programme. Next, the vacuum valve. Located on the carburettor above the stepper motor, this is connected to the rotary choke by an air supply port. Its function is to provide additional enrichment for acceleration during the warm-up period. A diaphragm within the vacuum valve is held on its seat by a coil spring. When manifold depression's high, the diaphragm is pulled off its seat, overcoming spring pressure. Air drawn through port 2 can now enter through both passages X and Y to give a relatively weak air-fuel mixture. When the throttle is opened, manifold depression falls, allowing spring pressure to return the diaphragm back against its seating, sealing passage X and therefore reducing the volume of air, which now enters through passage Y only, giving a richer mixture for acceleration. If acceleration is poor during warm-up, when the choke's in operation, or the car suffers from poor drivability from cold, make sure the air supply pipe from the vacuum valve to the carburettor isn't cracked, perished or loose. An air bleed at this point will cause an overweak mixture during engine warm-up. On the other hand, if the vacuum valve diaphragm was punctured, fuel will be drawn from the rotary choke via the air supply pipe and diaphragm into the manifold, causing over-enrichment, more pronounced during high inlet manifold depression conditions. A simple test of the diaphragm can be carried out by disconnecting and blocking the vacuum pipe. If the mixture immediately weakens, test the diaphragm using a vacuum pump. If the vacuum doesn't hold, change the vacuum valve. .3 and 2.6 twin carburettor models with fuel management have no vacuum valve. Additional enrichment for acceleration whilst the rotary choke's in operation is achieved by the ECU indexing the stepper motors a predetermined number of steps and then returning them to their original position over a short period. This occurs every time the throttle switch is operated until normal engine operating temperature is reached. The Rover 3.5 V8 uses this indexing method as well as the vacuum valve we previously looked at, whereas the 2-litre O-series engine, when fitted with twin carburettors, uses neither method, as the twin carburettor configuration on its own is sufficient to provide the necessary enrichment. The ECU also controls the fast idle and idle speeds through a push rod actuated by the stepper motor cam wheel. When the cam wheel is rotated by the stepper motor, the push rod moves, causing the throttle disc to open or close. The adjusting screw shown here is used to set the fast idle speed, which we'll cover later in the programme. Starting from the stepper motor rest position, the first 40 degrees of cam wheel rotation progressively increases the idle speed only. Further rotation of the cam wheel also starts to open the rotary choke to introduce additional air-fuel mixture. This first 40 degrees of cam wheel rotation provides two functions. Firstly, a fast idle speed used during the engine warm-up period, controlled by the ECU with signals received from the coolant thermistor. Secondly, the ECU provides an idle speed control through a throttle jacking facility. With a conventional carburettor, the idle speed is set higher than is desirable for maximum fuel economy to prevent the engine from stalling when any mechanical or electrical loads are applied. To enable the idle speed to be set at a lower, more economical level, the fuel management system operates the throttle jacking push rod on the carburettor to raise idle speed only when necessary. When the engine has reached running temperature and, for example, the heated rear screen is switched on, the additional alternator load may cause the engine speed to drop. The ECU senses engine speed from the ignition coil negative terminal. When the idle speed drops below the preset level, The ECU sends a signal to the stepper motor, causing the cam to rotate and move the throttle jack push rod, raising the idle speed by between 100 and 200 revs per minute and maintaining this increased idle speed for approximately 1 minute. So, to summarise, the stepper motor controls the throttle disc, providing two functions: to give a fast idle during cold running conditions and allow lower, more economical idle speeds to be set. Before going on to the fuel cut-off valve, here's a point worth mentioning if, for any reason, you're changing an ECU or suspect one's recently been changed. Make absolutely sure the correct unit is or has been fitted. If, for instance, an ECU intended to maintain the 1.6 automatic idle speed of 825 revs per minute is fitted to a 1.6 manual, it'll be impossible to obtain the correct idle speed of 750 revs per minute. Even if you completely undo the idle adjusting screw, the throttle jack, controlled by the ECU, will attempt to maintain the higher tickover, and the engine speed will constantly surge. So make sure you double-check the part number on the microfiche reader or service bulletin. Finally, we'll look at the fuel cut-off valve employed in the fuel management system. But before we do, let's establish why it's used. With a conventional carburettor, fuel continues to be drawn into the engine during overrun. This means that during deceleration, fuel is being wasted because not all of it is needed to drive the engine and produce power. With the fuel management system, however, the ECU controls the fuel cut-off valve, which reduces the flow of fuel to the engine during deceleration. Before the fuel cut-off valve will operate, however, certain conditions must be met. These are: ambient air temperature must be above 6 degrees centigrade, coolant temperature must be above 80 degrees centigrade, engine speed must be approximately 1300 revs per minute or above, and the throttle pedal must be in the fully closed position. Only when the ECU has sensed that all these conditions have been met will the fuel cut-off valve operate. This sectioned view shows the fuel cut-off valve under normal running conditions. The valve is operated by a solenoid and is located in the passage which links the venturi with the top of the float chamber. Under normal running conditions, the valve is in its off position, sealing the passage to the venturi. Air enters the float chamber through both the air restrictor orifice and also through the passage underneath the valve. In this position, atmospheric pressure acting on the fuel allows it to be drawn from the jet as required. When the conditions necessary for valve operation are satisfied, the ECU passes current to the solenoid, which is then energized, operating the cut-off valve. Air can now only enter the float chamber through the restricted orifice, arrowed here on the left. Movement of the valve also opens the passage between the float chamber and the venturi to draw air out of the float chamber. As only a limited amount of air can enter through the restricted orifice, atmospheric pressure above the fuel is reduced, and therefore less fuel can be drawn from the jet. The operation of the fuel cut-off solenoid is continuous on some models, whereas on others the ECU opens and closes it for short periods only, with the duration varying between models. If the valve sticks in the operating position, fuel cut-off or fuel reduction will be continuous, causing the engine to run or attempt to run with a very weak mixture, resulting in a poor tickover and difficulty in starting. On the Montego and all other models where fuel cut-off is off and on, a simple way to test the fuel cut-off is as follows. With the engine at normal operating temperature, move the carburettor linkage to raise the engine speed to above 1300 revs per minute and hold it steady. Don't use the throttle pedal. Because the throttle pedal switch is in the off position, the ECU assumes the engine's on overrun and for 9 seconds will attempt to purge the engine, indicated by the engine speed rising and falling. If this doesn't occur, the fuel cut-off valve should be checked further using the fuel management fast check, which we'll come to later in the programme. Well, that's covered the operating principles of the fuel management system, and whether the system is of single or twin carburettor configuration, a full understanding of how it works is essential. Before going on to section 2, which deals with the adjustment and tuning of single carburettors, stop the tape and answer the series of questions in section 1 of the accompanying workbook. When you're ready, start the tape again to resume the programme. As with the previous section, we'll be using a Montego S-Series engine, but before attempting any tuning adjustments, ensure that the ignition, distributor and spark plugs are functioning correctly. And remember, incorrect tappet clearances can also affect engine tune. These checks may seem obvious, but could save you valuable time in the long run. Starting with the basic settings, remove the plenum chamber. Remove the suction chamber and check that the needle guide is secure and flush with the piston face. Turn the mixture adjuster screw to bring the jet flush with the bridge, then turn the adjuster 2 turns clockwise. If the vehicle's covered a very high mileage, check that the jet's not worn oval. If it is, change both needle and jet. Next, make sure the throttle operates correctly and that the cable has 1 mm free travel. Refit the suction chamber assembly less the damper, taking care not to wind up the piston spring. Lift the piston and check that it falls freely onto the bridge. If it doesn't, investigate further. Top up the damper tube with engine oil to the correct level and refit the damper and plenum chamber. Make sure there's a clearance between the throttle lever and the lost motion link. After making sure all electrical equipment is switched off to prevent alternator loads, which could affect idle speed, start the engine and turn the idle adjustment screw until the engine is running at 1500 revs per minute. Keep the engine running until normal operating temperature is reached. That is, when the cooling fan has operated at least once. Then run it for a further 5 minutes. Now increase the engine speed to 2500 revs per minute for 30 seconds to clear the carburettor of warm fuel. If tuning adjustments have not been completed within 3 minutes, repeat this clearing operation. After ensuring the cooling fan has cut out, begin tuning by turning the idle adjusting screw to obtain the specified idle speed, making sure you always reduce the speed to the required idle setting. If you try and start from a lower than normal speed, the ECU will commence throttle jacking. If throttle jacking does occur, increase the idle speed and wait 2 minutes for conditions to stabilize before resetting the idle speed from the higher position. Now check the CO reading, adjusting the mixture screw as required, turn clockwise to richen the mixture and anti-clockwise to weaken it. Then reset the engine idle speed. Now, set the throttle lever at the fast idle position by disconnecting the coolant thermistor multiplug. Check the fast idle speed against the figures given, turning the adjustment screw to obtain the specified fast idle speed. An important point to remember, on early A&R series Maestro models having an ECU identified by a suffix A or B after the Lucas part number, fast idle setting is carried out after disconnecting the ambient air sensor, linking the harness connectors together and disconnecting the coolant thermistor. Connect the fuel management fast check. In the case of a 1.6 engine with an A or B suffixed ECU, or a 1.3 engine with a B suffixed ECU, move the selector switch to the 600R position. Whilst in the case of a 1.3 engine with an A suffixed ECU, move the switch to the 1K position. So to summarise, The selector switch should be moved to the 600R position for a 1.6 engine with an A or B suffixed ECU and a 1.3 engine with a B suffixed ECU, and moved to the 1K position for a 1.3 engine with an A suffixed ECU. A quick method of identifying these early vehicles is by disconnecting the coolant thermistor multiplug. If the engine starts to hunt, this indicates that the stepper motor has moved to provide full choke condition. Whereas on later models, disconnecting the coolant thermistor multiplug will give a fast idle position only, but no choke. However, in order to check stepper motor operation on these models and make sure full choke position is obtainable, connect the fast check and move the selector switch to the 30K position. Now, returning to the S-series engine, reconnect the coolant thermistor multiplug and recheck that the CO reading and idling speed are correct. Switch the engine off and remove instruments. Finally, set the lost motion link by turning the throttle lever adjusting screw to obtain a gap of 1.8 millimeters, plus or minus 0.25 millimeters. That completes the tuning and adjustment of the single HIF44 carburetor with fuel management. Before going on to section 3, which deals with the adjustment and tuning of twin carburetors, stop the tape and answer the series of questions in section 2 of the accompanying workbook. When you're ready, start the tape to resume the program. In this section, we'll be using the 3.5 Rover as our example, although the remarks apply equally to the other SD1 Rovers fitted with fuel management. You should refer to the relevant manual to check for any differences in tuning settings or component locations that may exist between models. Some of the tuning procedures will be common with those already covered earlier for single carburetor application, but for clarity we'll now run through all the stages necessary to set the carburetors on a 3.5 Rover. First, ensure all electrical equipment is switched off. Then disconnect and remove the air cleaner assembly. Now remove the coolant thermistor multiplug and bridge the two terminals. Switch on the ignition. This ensures the mixture controls are in the fully off position. Now switch the ignition off. Check that the throttle functions correctly and the cable has 1 millimeter of free travel. On the 3.5 Rover, disconnect the throttle interconnecting rod. Next, unscrew both idle adjusting screws until they're just clear of the levers. Then turn the screws clockwise until just touching the levers, and then a further 1.5 turns to give the initial idle setting. Taking each carburetor in turn, we'll continue as we did previously with the single carburetor. Remove the suction chamber, check that the needle guide is flush with the piston face and is secure. Turn the mixture adjuster screw to bring the jet flush with the bridge, then turn the adjuster 2 turns clockwise. Refit the suction chamber assembly less the damper, taking care not to wind up the piston spring. Lift the piston and check it falls freely onto the bridge. If it doesn't, investigate further. Repeat these operations with the other carburetor. Top up the damper tubes with engine oil to the correct level. Refit the dampers and reconnect the coolant thermistor multiplug. After connecting the engine tester, start the engine and turn the idle adjustment screws equally until the engine is running at 1500 revs per minute. Keep the engine running until normal operating temperature is reached, then run it for a further 5 minutes. As with the single carburetors, make sure there's a clearance between the throttle lever and the lost motion link. Now adjust the idle screws on both carburetors an equal amount to the recommended idle speed. As we mentioned earlier, to prevent the ECU operating the throttle jacks, the idle speed must always be adjusted down from a higher speed and not allowed to fall below the recommended speed during setting. If throttle jacking does occur, turn the idle speed adjuster to increase idle speed, then wait 2 minutes for conditions to stabilize before resetting the idle speed from the higher position. Next, carry out the clearing operation as before by increasing the engine speed to 2500 revs per minute for 30 seconds, and repeat this if adjustments have not been completed within 3 minutes. Using an airflow balance meter, check the synchronization of the carburetors. Adjust the idle speed screws to obtain equal readings. Now, treating each carburetor separately, turn the mixture adjusting screw until the fastest engine speed is obtained. Then turn the screw anti-clockwise until the speed just begins to fall, and then clockwise just enough to obtain the fastest idle speed. Readjust the idle speed using the idle adjusting screws by small equal amounts. Using an exhaust gas analyzer, check the CO reading and adjust the mixture screws on both carburetors in 1/8 turn steps until the correct reading is obtained, pausing after each adjustment, allowing time for it to take effect. Clockwise to enrich, anti-clockwise to weaken. On the 3.5 Rover, reconnect the throttle interconnection rod, increase the engine speed to 1500 revs per minute, and check for throttle synchronization using the airflow balance meter. If adjustment is required, turn the interconnection lever adjustment screw until the left-hand and right-hand throttles open together. Ensure that there's free movement in the throttle linkage before the throttles start to open. Switch off the ignition and check the clearance between the throttle lever and the lost motion link, adjusting the screw to obtain the specified clearance. Now disconnect the coolant thermistor multiplug and start the engine. The throttle jacking push rods will have now moved to the fast idle position. Using an airflow balance meter to ensure the carburetors remain synchronized, turn the adjusting screws to obtain the specified fast idle speed. Switch off the engine, connect the coolant thermistor multiplug and fit the air cleaner assembly. Restart the engine and make a final check that the CO reading and idle speed are correct. That completes the tuning and adjustment of twin HIF carburetors with fuel management. Before going on to section 4, which deals with fast check diagnosis and testing, stop the tape and answer the series of questions in section 3 of the accompanying workbook. When you're ready, start the tape and resume the program. System testing is simple and carried out with the fuel management fast check, which uses the proven principle of go, no-go testing. The fast check is connected into the system in place of the ECU and operates by illuminating, or not illuminating, a series of light-emitting diodes, or LEDs, thus enabling the major electrical circuits in the fuel management system to be tested. But before condemning the fuel management system electronics, first ensure the problem is not merely a case of poor engine tune or simply a disconnected wire. Fast checking procedures are virtually the same for both single and twin carburetor installations. We'll therefore use the S-Series Montego to go through all the fast check procedures and cover any additional points applicable to the twin carburetor models at the end of the section. Now, an important point to note here is that whenever a vehicle is fitted with programmed ignition, the programmed ignition ECU multi-plug should be disconnected before any fuel management fast check tests are commenced. If this step is not taken, the coolant temperature sensor circuit will not be monitored during the fast check test procedure. Let's start by carrying out a system test as an example to show how easy the fast check is to use. Lower the ECU from its mounting, disconnect the harness connector, and then connect the fast check in place of the ECU. When the ignition is switched on, the ignition, throttle, and coil LEDs should illuminate, while all other LEDs remain off. Now press the accelerator pedal. The throttle LED should go out. Next, take the fast check to the engine compartment. Move the solenoid selector switch from the off to the on position. The fuel cut-off solenoid should be heard or felt to operate. If the correct response is obtained by the fast check, this indicates that all the inputs are satisfactory. But before condemning the ECU, check that the ECU terminals are not corroded or dirty. Then retest the vehicle to see if the fault has been rectified. If the correct response is not obtained by the fast check, disconnect the harness from the fast check and ensure the harness terminals have not opened out. If they have, very carefully squeeze the terminals together using pin-nose pliers and then, most important, retest the system. Now let's see how easy fault diagnosis is using fast check. Suppose the coolant LED is illuminated. This indicates a high or low resistance exists somewhere in the coolant thermistor circuit. In the case of a high resistance, the choke could remain on, causing a rich mixture, whereas a low resistance could cause reduced choke movement, contributing to poor cold starting. Now that the faulty area has been highlighted by the fast check, you can test the continuity between the appropriate ECU multiplug terminals and the thermistor multiplug using an ohm meter. If you don't find a continuity fault in the circuit, the coolant thermistor is faulty and should be replaced. The air temperature LED should also be off. If it's illuminated, this indicates a fault in the air temperature circuit, and it should be checked using the same procedure we've just gone through with the coolant temperature circuit. If in this case a high resistance exists in the circuit, overrun fuel cutoff would not occur, whereas a low resistance could prevent additional choke during extreme cold conditions. Let's assume the ignition LED doesn't illuminate when it should do. This indicates there's no electrical supply from the ignition switch to the appropriate terminals on the ECU multiplug. You'll also find the throttle LED will not be illuminated. A fault in the main electrical supply will prevent the stepper motor from operating. As before, test and repair the circuit as necessary. The coil LED, however, should be illuminated. If it's not, this indicates a fault in the wire from the coil negative terminal to the fuel ECU, in which case throttle jacking and overrun fuel cutoff would not occur. Let's suppose the stepper high LED glows when it shouldn't. This indicates a high resistance in the stepper motor circuit. To test further, disconnect the stepper motor multiplug and contact the ohm meter probe with the stepper motor common terminal, which is easily recognized as it's offset from the rest. Then check in turn the resistance between this terminal and the remaining 4 earth return terminals. If any of the readings are above 18 ohms, the stepper motor is faulty. If, on the other hand, no fault is found, then a harness fault exists between the stepper motor and ECU, which should be tested for continuity and faulty connections rectified as necessary. Should the stepper low LED glow when it shouldn't, this indicates a low resistance in the stepper motor circuit. As before, check the resistance between the common terminal in the stepper motor multiplug and each of the 4 earth return leads. If any of the readings are below 12 ohms, the stepper motor is faulty. If no fault is found, then a harness defect exists and again will require tracing and correcting. Now the throttle LED. If this is not illuminated with the throttle pedal off, it indicates that the throttle switch contacts are not closing and will prevent overrun fuel cutoff from being implemented. Check the switch and wiring. Alternatively, if the throttle LED is illuminated when the throttle pedal is released, but will not go out when the pedal is depressed, the switch contacts are not opening. This will show up as an engine hesitation and surge at speeds above 1300 revs per minute. Finally, the solenoid switch. If the solenoid doesn't operate when the switch is moved to the on position, first check the wiring continuity. If this is okay, the solenoid is faulty. If all the fast check tests have been completed and the fault still can't be traced, consult the repair manual to make sure the correct wires are connected to the correct terminals in the ECU multiplug. OK, that's covered fast check fault diagnosis on single carburetors. Exactly the same procedures apply to twin carburetors, with the exception of 1 or 2 additional points, which we'll look at now. Only one stepper motor and fuel cutoff solenoid circuit can be tested at a time. Therefore, before you start system testing, disconnect the stepper motor and fuel cutoff connectors from one carburetor. Then carry out a system test using the same procedure as we did for the single carburetor. Once the test is complete and the first carburetor is reconnected, the second carburetor can be disconnected and the test repeated. A point to mention here is if the vehicle has cruise control fitted. Both fuel cutoff solenoids will be disconnected and their harnesses either taped up or removed. This is intentional, and the solenoids should not be reconnected or fuel cutoff could be activated whilst cruise control is in use. Refer to your repair manual for the remaining component checks you should follow in order to test the entire fuel management system. OK, that's covered the main points on the Austin Rover fuel management system. A system, incidentally, that's highly regarded throughout the industry. But like everything else, it's only as good as its weakest link, including the service backup. Don't let that weak link be you. Let's be fair, it is a complex subject, both for us to put across and for you to fully understand. We hope this Service Insight program has benefited you. By always referring to your repair manual and fully understanding how the system works, how to diagnose, test and rectify possible problems in service, you'll be able to approach the subject with confidence. If there's any part of the program you're not too sure of, do take the opportunity and go through the relevant section again. Now you've come to the end of the program. Stop the tape and refer to the questions in section 4 of the accompanying workbook.